Hello and welcome to the lecture on augmented reality. Today's topic is object pose estimation. Here we will not only cover pose estimation but also the task of object detection. For this we will proceed as follows. First we will talk about fiducial marker detection, which is an easier task because we can design the markers in a way that is easier for us to detect. Next we will turn to natural feature detection, which is slightly harder because we have to deal with arbitrary images and have to detect them. And finally, we will move away from detection towards tracking. And specifically, we will talk about contour-based tracking based on the silhouette of an object or a marker. So let's continue with fiducial marker detection. For this, let's take a look at the following image. Here we use fiducial markers, which you see on the sheet of paper, to detect the pose of the car, which is placed in the center region of the sheet, so we know how it is positioned relative to the markers. But first we will focus on the markers. So let's take a look at one of them, let's say this one, and note that they are all square black rectangles, and they have a specific black and white pattern inside. And the pattern is used to describe each of the markers. So each marker has a different pattern inside. We will talk about how to decode this later. But first, let's talk about how can we detect these rectangular shapes in the first place. Here we convert the image into grayscale first, like this. It makes processing slightly easier for us because now we only have to deal with a single luminosity channel instead of three color channels, and as the markers are black and white, we do not lose any information regarding to the markers. But as you can see with the car, we do not know which color it is anymore. However, turning it black and white did not make the detection task any easier so far. So the markers do not stand out notably compared to the previous image. To ease this task, we have further binarize the image. That means that we turn it not into grayscale but into only black and white. For this, the easiest approach would be to define a threshold, and below the threshold everything is black, and above the threshold everything is white. And this is what you see on the next picture. We define the global threshold, and in this case this is inverted, which means everything below a threshold is white and everything above a threshold is black. This is because we are interested in the markers, which are black, and yeah, we want them to glow in the dark, so to say. But this image shows a problem with this global thresholding approach. While it works for some markers, like this one on the far left, the markers in the center regions are cut. This is because a single threshold is not valid for the whole image. Specifically, if we talk about these markers close to the car, the parts which are white here, they are below the threshold because they are in the shade casted by the car. And if the shade is gone, then it's too bright and it's considered black. So in presence of lighting and shadowing and all these effects that change brightness, a single threshold does not work for the whole image. Instead, we want to look at the small region of the image and then say, okay, we define only a threshold for this region and then a different one for this region. It's like, yeah, a locally, a spatially varying threshold. And this is what we've done on the next slide. Here we define one threshold per 3x3 region of pixels. So for each 3x3 region, we compute the mean and then compare the pixels whether they are brighter or darker. And if they are darker, it turns white, and if they are brighter, it's black. And as you can see, we now see all the markers in the image. However, we do not see them clearly. As you see here, the contour of a marker is broken, in this part, and here it's also not that clear as it used to be. And furthermore, note that in homogeneous regions, which are all white, we have there are no pixels which are brighter or darker than the mean. Therefore, everything is black. And the same is true for regions which are all black. The mean is also equal to the values of the pixels. So we only see the edge pixels of a marker. But this is okay because we are only interested in the outer edge of the marker. So yeah. How can we solve the situation that the contour is not clear? We can simply increase the block size, which we see on the next slide. Here we are no longer considering only a 3x3 region, but a 13x13 region, which means that the mean we are computing is more meaningful. So we are now clearly seeing the contour of the marker, and it is true for all markers on the sheet of paper. So this is like a good approach to detect the markers. The next step is to detect all contours in the image which are convex and consist of exactly 4 corners, which pretty much defines the markers here. And this is what you see on the next slide. Here, each contour which satisfies this criterion is drawn with a different color. And as you can see, we have most of the markers colored, but also some inner regions or regions in the tire of the car, which are like not markers. So next we want to filter out these false positives here and only keep the actual markers. And this is where the inner part of the markers comes into play. So for looking in the on the inner part, we go back to the grayscale image here, but we keep the contours we detected. And now we take advantage of our prior knowledge that a marker is a square. And because we now know the contour in the image, we can compute transform such that the marker becomes square again. And this allows us to remove any perspective effect we have in the image, which in turn eases the decoding of the inner part. So yeah, we want to do this in the following. For this, we consider this marker here and remove the perspective like this. As you can see, the marker is slightly rotated compared to the image, like it was like this, and now it is like this. But this is not an issue for us for now. So now that we have removed the perspective, we can start decoding the inner part of the marker. Here we first remove any border pixels like this black border because it does not contain any information, and it might be slightly off because if we did not properly draw the contour, there might be some noise in this border. So this is what we do next. And we for the inner part, we then overlay it with a grid. In this example, we choose a 4x4 grid, and this is like also prior knowledge because the markers are designed to contain only 4x4 black and white pixels. And with this grid, we then again look at the center area of the grid and determine whether it's rather black, like in this region, or rather white, like in this region. This allows us to assign to each grid cell either a 0 or a 1. And this is what you see on the bottom here, where we traverse the grid row-wise and then just written down whether it's 0 or 1. So if it reads like this, the first row is 0, 0, 1, 0, and then the next row is all ones and so on. We can then turn this rather long binary string into a more compact hexadecimal representation, where each row is represented by exactly one character. So like this row is like 16 and this row is 2. And this is what you see in here. So what this allows us is to assign one number to each candidate. And we looked at a real marker. So let's try to see what happens for a false positive. For this, we look at this quad over here, which is clearly a false positive. And when we do the same like we did previously with this marker, we get this, like it was all black, so we cut off the borders, overlay with the grid and decode it, and this false positive decodes to 0. So we can now use these numbers describing our detections to say whether it is a real marker or if it's a false positive. For this, we simply define a dictionary of all valid numbers, which corresponds to the markers which are valid, and every number which is not in the dictionary is then a false positive, and we discard it. But let's take a closer look on such a dictionary. So in our case, it includes this number of the first marker we decoded, and it excludes this 0 detection. However, this codes which are included are not like arbitrary numbers, but they have a special properties. And one property is that they are rotationally variant. This means that if we rotate the marker by 90 degrees, for instance, or 180 degrees, the decoded number is a different one. And we require this because we later on want to use the markers to compute a pose, and here it makes a difference where or how the marker is oriented. And notably, this 0 decoding is rotationally invariant. Like if you rotate the totally black marker by 90 degrees, it still decodes to 0. So it's another reason why 0 is a like bad code and should never be included. Furthermore, there's another important property of a good dictionary, and it is that the Hamming distance of all markers or all codes inside is maximal. So first, maybe let's recap what a Hamming distance is. For this, here. Let's take a look at this binary string. And a Hamming distance computes a distance between two binary strings. So imagine there's another binary string below. What the Hamming distance computes is an XOR between all the bits and then sums up all the ones in the XOR result. Or in other words, it counts all the bits where two binary strings are different. So coming back to this slide, if we have different markers in our dictionary, then we want the Hamming distance to be maximal between them. This is called intercode distance between different markers, and this avoids confusing different markers. So imagine we have two markers where the Hamming distance is 1, so they are only different in 1 bit of the decoded code, and then we have an error in the decoding because there's some noise or some shadow on the marker, and then the bit is wrong. Then we might confuse these two markers, and having a larger Hamming distance between two markers avoids this. However, there's also an other distance, which is the intracode distance, which we want to maximize, and this is the codes which we get by rotating a marker by in 90 degrees steps. So this is coming back here. If we rotate a marker and then the resulting number only differs by 1 bit, we again are in the same situation like here, and then we confuse the rotation of the marker. So the same argument applies. If the code is significantly different under rotation, it's a good property. And if we now further assume that the minimal Hamming distance between two codes or two markers is at least 3, like 3 bits are different, we can now implement error correction. So let's think of we decoded a different number than this, which is different from this by 1 bit. So let's say we have a 5 in this place instead of a 4. If we know that the minimal distance between different rotations and markers is at least 3 bits, then we can safely say that although we decoded a 5 here, this must be this code. Because it's only 1 bit away, or a Hamming distance of 1 to this code. And because the distance to all other codes is at least 2. So yeah, having a maximal Hamming distance is a good property and allows for error correction. And if you want to know more details about how to design such a dictionary, I refer you to the paper cited below. And if you just want to use a good dictionary, the predefined dictionaries in OpenCV are actually based on this paper. So if you choose any dictionary in OpenCV, it has these properties. Of course, the smaller the dictionary is, the larger the maximal Hamming distance can be. So if you only have 2 markers in a dictionary, they can be further apart than if you have to squeeze in like 1024 markers in the same code. Okay, now that we know how to identify the markers, let's do this on our example, which you see here. Note that the ID which is given here is the position in the dictionary and not the actual code, because like set 0 is a bad code, and 1 is as well, and we have like 1 and 2 here. Also see that all markers have the lower right corner marked, and this shows that they are correctly, that the rotation of the marker is correctly detected. However, so far we are only in 2D. So this green outline is only a 2D contour. We still do not know the 3D position and orientation of the markers. And given this green contour, or the 4 corner points of the marker, we want now to compute the orientation and location of the marker. This leads us to the following problem. We are given like the 2D locations of the corner, and we assume we know the respective 3D coordinates of the corners. So this problem is the PNP, perspective endpoint problem, which we briefly covered in the last lecture. And we can solve it with this OpenCV function. Let's briefly talk about the parameters. So we have the intrinsic matrix and the distortion coefficients back here, which we talked about last lecture already, so I don't go into details here. Then we have the known 3D coordinates. Here we can just use any square arrangement of 3D points. So here we used these. The important thing is that the marker is planar, so one dimension must be 0. Here it is the Z dimension, but you could choose any other. And the value for the size doesn't actually matter, or it merely determines the unit of the translation vector. So the 3 here can mean 3 millimeters or 3 meters, or if you write 30 here, then it would be again either 30 centimeters or 30 meters. You can just as good scale the translation vector you get out of the function to change the unit. The only thing that is important that this is the square. And the last parameter are the 2D points, and as I said already, it's just the output of our marker detection. It's the 4 corner points of the contour. And all the parameters except the 2D points are fixed. So the 3D points we assume given, and the calibration parameters we also assume given or fixed from prior calibration. So let's take a closer look at the 2D points. Yeah, here we look at the marker in the far left corner of the image, and in blue we have marked the detected corner points of the contour. And because this position directly influences our resulting pose, we want them to be as good as possible. And if we look at this corner, we can say, okay, it's quite nice. So it's like the crossing of these two lines. We are about here. But for this corner, we are not so sure whether this is the best location we could get. And indeed, we can try to improve this location by applying a method which is called Subpixel corner refinement. And this is the result. I toggle back to the previous slide. This is the initial location, and these are the refined location. And indeed, specifically looking at this corner, it seems like we now arrived at a better location. But how did we do this? Well, in short, we took a look at the image gradient and moved to a location where the gradient becomes 0. So yeah, first let's talk about the gradient and look at this image here. The first thing to note is that the gradient has 2 dimensions. In this case, the image x-axis and the y-axis. And yeah, we want to move somewhere where the gradient becomes 0. So let's say we start somewhere here, then the gradient points in this direction, and we move in this direction until we are outside of proximity of this edge over here. But because we consider both directions, there's also the gradient in the y direction. So given we started here, we would move somewhere along this line until we moved past the corner where we do not see the gradient anymore. And this is also the explanation why we use the chessboard pattern for camera calibration instead of simply quads, because with the quad we always move outside of the true corner position. So given we start at the corner position, here is the gradient, and then we move outside the proximity. And we will define what proximity means shortly. But if we look at the chessboard pattern here, there we have gradients which cancel themselves out, like this one and this one and this one and this one. So if we are at the true crossing point, then the gradient already vanishes because of this cancellation over here. Okay, let's talk about the equation, how this is computed. The idea is that the direction where we want to move, let's say we start at the point P0 and we want to move to the crossing point over here, then this vector is orthogonal to the gradients in the local proximity, which means that this dot product between the gradient and this vector over here must be 0, and this is what we also want to minimize. Note that the gradient is given and the point is given, so we are optimizing for the Q. So we do not know the true position of Q, but rather want to go from here along the or orthogonal to the gradients in this direction. Yeah, and this is a good opportunity to talk about the definition of proximity, because it also affects how far we can go into the or along orthogonal to the gradient. And proximity is again defined by the support region, which is just a window around this point where we start. And yeah, as you see here, if we select the support region too small, then we only see white pixels here, so there is no gradient and we do not move. On the other hand, if we select the support region too large, then we move too far away in this case. So if this is like a huge support region, then we see this gradient even if we are here, so we have to move here to until the gradient becomes 0. Which is of course a lesser problem in here. So if we take a look at the calibration setting, which we talked in last lecture, then recall this yellow region is the magnitude of the gradient. And as you see, this one would push us out away from the real corner. But in this case, this magnitude would cancel itself out and we would stay here. So yeah, this is why we use the chessboard pattern. And with this information we collected so far, we can now go back to our example image and compute the pose for the individual markers, which looks like this. So as you can see, the markers are in the XY plane, similarly to how we showed the 3D coordinates in the example. However, the origin is not a lower left or right corner, but rather the center of the marker. And the poses you see here are computed using the non-refined position. If we apply subpixel refinement, then we get these poses. And as you can see, for instance, in the marker we zoomed in on before, this is the unrefined pose and this is the refined pose, and the refined pose seems to be a little bit more accurate. Also note the marker over here. In the refined pose it seems fine, but in the non-refined pose the Z coordinate seems to be flipped. So yeah, this is the correct one and this is the incorrect one. And you might think, okay, this is the effect of the subpixel refinement, it corrected our pose, but actually the error you see here can also happen with the refinement enabled. And this is a different issue you see here, and we come back to it on the next slides. But first let's turn back to the car, which I talked about earlier. Now that we know the pose of all markers, we also know the pose of the car, and we can actually do what we initially wanted to do, which in this case is reconstructing the texture of the car, which you see here. So everything starts with a black surface, and as soon as we see the actual surface, we start filling up the texture map of this model. And this is like the task we wanted to achieve, and the markers allows us to do it. So we can focus on something else and forget about the pose estimation of the camera. Yeah, this is mainly meant as a small teaser, so you see what is possible to do with the things you learned so far. Let's turn to natural feature detection now. Here we no longer want to detect the simple black and white markers we talked about so far, but rather we want to detect arbitrary images. So let's say we want to detect this image in arbitrarily placed in the camera frame. So this is like the template, similar to the marker where we remove the perspective. How can we do this? The trivial idea would be to go for the corners again. So let's say we want to detect the corner and this corner. However, if you take a look at the contrast between the corner and the white background of the slide, it's probably not going to work out very well. Instead, we have lots of contrast inside the image, and this is what we want to use. So the first task is to detect the appropriate corners inside the image and what is an appropriate corner. We will answer this by using the Harris operator, and you see the results here. If you want to know more how the Harris operator works, take a look at the link below. In short, it's very similar to how subpixel refinement works. It computes the image gradients, but instead of looking for regions where it's 0, which are gray in here, it looks for regions where the gradient is maximal. And not only in one direction, but in 2 directions, because this is what defines a corner. So yeah, again, look at this tutorial. According regions are marked white in this view. Probably you cannot see them pretty good, so therefore I mark them with circles, which you see here. So yeah, let's take a look at this circle and switch back. There's a white pixel, and now yeah, these are the maximal locations. So instead of detecting the corners of the image, we are going to detect this circled pixels in a camera frame. However, the Harris corner detector is rather slow to compute, because internally it computes the eigenvalues of the structure tensor, which is densely of on the whole image, and yeah. Nowadays one would instead use the orb detector in descriptor, which you see on the next slide. So in blue now are the pixels which are detected by the or chosen by the orb detector. And if you I switch back and you take a look at this region here, it's pretty similar to what Harris would do, but orb is much faster. So let's talk about orb in more detail. First of all, orb defines a detector and a descriptor. So we should think about what's the difference between these two. Yeah, a detector is an algorithm which finds points of interest in an image. And points of interest is not something that is particularly beautiful, but rather something that you can find reliably. And an example for this is like the Harris corner detector, which you see previously, or with the markers, it was the contour, which we use to detect the markers. Descriptor, on the other hand, tries to describe these corners or the points of interest as uniquely as possible. Yeah, the point neighborhood, and in this case, it's orb. And with the markers, it was the code inside the markers which was describing the markers. Okay, so how do the detectors and the descriptors of orb work? The detector of orb is oriented fast. Before we turn to the oriented property of fast, what is fast? Basically, it's a very simple approach, and yeah, look at this image patch, which is magnification of this one. And given 1 pixel, look at the circle at a given radius around the point. And then we start at some pixel and say, okay, is this brighter than the center pixel? And if we say yes, we start counting how many of the following pixels are also brighter. And the number of pixels we counted is the fast score for this point. So it answers the questions, are n pixels brighter than the center pixel p? And if you think about it, it's pretty similar to what the Harris corner detector would do, because the number of bright pixels defines the angle of around this corner. And the Harris detector wanted to select points where the gradient in 2 directions is strong. So like this direction and this direction. And with the fast detector, we can describe a similar thing by ensuring how many of the pixels are brighter than the center. If there are only a few pixels, like in the edge area here, then we would discard this point. And while this might seem to be a rather tinkered solution, it in practice works very similar to the Harris corner detector. Okay. Now let's consider the oriented property. Here one basically remembers the brightest pixel. So let's say the pixel number 1 would be the brightest pixel. It would then define the up direction of the whole patch. So if we rotate the patch of, let's say, 90 degrees counterclockwise, and the brightest pixel is now here, then the up direction would be then to the left instead to the up. So this allows us to orient the patch in a standard way. And we will need this with the descriptor, which is a good transition. With orb, the descriptor is rotated brief. First, a descriptor tries to describe this patch as uniquely as possible, and brief does it as following. It randomly samples pairs of pixels inside this patch and then stores whether the first pixel was brighter than the second one. And in the original brief paper, it was like 128 samples, which was then the descriptor. And as for each pair, only the information is brighter is stored. It's only a binary vector of 128 values. Yeah. The question is now how to sample these 2 points. In the brief paper, they tried several approaches. This one is uniformly sampling the coordinates, which you see here. And then they also tried using the standard distribution, like the Gaussian, to sample the locations, which you see in the remaining images. And as you can tell by the amount of Gaussian sampled locations, they went with the Gaussian sampling. And in this image, they also enforced that the first pixel is always in the center. So this one actually resembles the fast detector. And after the evaluation, they actually went with this variant here. Of course, once you sampled this location, you keep them fixed and use them for all your points. So you have a chance to find it back. However, as one can think, this thing over here is not rotationally invariant. This means if you rotate your image by, let's say, 90 degrees, you cannot find back your patches anymore, which is solved by using the orientation we computed with oriented fast. So with this patch, we know a canonical up direction, which is given by the brightest pixel. And now we can use it here to rotate the patch such that the brightest pixel is always up and only then compute the descriptor, which makes this rotation invariant as well. The advantage of this approach is, as noted, that the descriptor is a binary string. So we can again use the Hamming distance for comparison. And it's particularly fast because modern processors have a hardware instruction to compute a Hamming distance between two vectors. And typically you can do this between 1 and 2 cycles. So with ORB, we only have binary pixel comparisons. So with fast, we compare the center pixel to its surroundings, and with brief, we compare arbitrary pairs of pixels. And we do not have to compute any gradient or any eigenvalues, and this is what makes ORB particularly fast, but still it's quite robust. So let's try to use it with our example image for natural feature detection, which you see on the following slide. Here we first applied the ORB detector on our template image on the right and selected some key points. And then we applied the ORB detector on our camera frame here and also selected some key points. And after this, we used the ORB descriptor to match these points up. Here we not only consider the closest match, but also the second closest match. This is why it's called KNN2 match, so it's two nearest neighbor. And this is why we have so many lines over here. So each point on the right is connected to two nearest neighbors on the left. And as you can see, these lines cross all over, which means that we did not match it particularly good, because if everything would be correct, the lines would be mostly parallel to each other instead of crossing. So how can we clean up the situation? Well, we can take advantage of the fact that we matched the two nearest neighbors as follows. We can now remove ambiguous matches by doing the ratio test. And the ratio test compares the best match to the second best match. And it does so by computing the ratio and looking whether it's below a certain threshold. And in this case, we keep the match. So let's consider the cases where we keep the match. The first case is that the best match is really good, like it's close to 0 or 0. This means we are pretty certain about this one. And the second case is when the second best match has a really large distance. So it means that this one is really uncertain. And notably, it excludes all cases where the first match and the second best match are pretty similar. So imagine the first match and the second match only differ by 1 bit. And this is the same argument which we made with marker detection. Then it might be only noise or a bad measurement which made this the first and this the second. And this means the whole match is uncertain and we should discard it. So this is the idea of the ratio test, and you can see the result on the bottom here. And as you see, we got rid of most of our matches because they were ambiguous. And the matches we kept are pretty good. As you can see here, there are only a few lines crossing the other lines. So all parallel lines belong together. However, we want to get rid of those outliers as well, and we do it using RANZAC. So what was RANZAC again? RANZAC is a certain algorithm where you try to compute a solution only selecting a subset of samples. So in this case, we would select only like 3 correspondences between these images and then compute a solution. And using this solution, we would compute an error for all points. And then we would select randomly a different subset. And we do it for a few times and remember the best solution, which gives the overall smallest error. And the winning solution is then the one which does not include any outliers which break our solution. The question is now, what are we solving for during RANZAC? And the answer is we are computing a homography transform between these 2 images. So what is a homography transform? Let's take a look at it on the following slide. Generally speaking, a homography is a mapping from one plane to another. And in terms of perspective endpoints, is a singularity, like a special case, which cannot be handled by the general perspective endpoint formulation, because due to all points being coplanar, one dimension vanishes and cannot be determined anymore. Therefore, most perspective endpoint implementations have a check whether the points are coplanar and then fall back to a different solver. And one possible fallback would be using a homography. So again, what is a homography? It's generally speaking a 3x3 matrix which only has 8 dimensions of freedom. And yeah, like said, it's capable of mapping arbitrary planes between each other. So if we take a look at this schematic over here, we have a, let's say, table here, and then we have a picture from this perspective and this perspective. So a homography can compute the mapping of the table in the image 1 and as well in the image 2, but it can also compute the mapping between image 1 and image 2, because all these are planes. Most notably, homographies are used for panoramic stitching. For capturing a panoramic image, you are assumed to stand at some point and then rotate like this, and capturing several images. So panoramic stitching then means transforming all these images into a single plane. And in this case, we would transform this, the leftmost image to the center plane and the rightmost image, which you see then below. Of course, there's more to panoramic stitching, but homography is a central part of it. So what do we get if we compute the homography in our example? Well, we get this. Here you see the camera view, and in blue you see the edges if we transform the corner points of our template view into the camera. And as you can see, this homography seems off a little bit, because you have like it doesn't fit in this region or in this region. So what did we do wrong? Well, we computed the homography by simply feeding in the points we detected in this frame. However, the camera has some lens distortions which are non-linear, but the homography computation is linear, so they were not considered. So instead of simply feeding in this 2D points we detected in the camera frame, we need to undistort them first, which we've done for this slide. And as you can see here, the blue frame fits much better. So the bottom line is that you always need to think about whether you have lens distortion or not, and you always should calibrate your camera so you have a precise solution. Okay, how can we now turn this blue frame into a pose, namely into rotation and translation, which you see here? Because we are faced with a slight issue here, as the homography has 8 degrees of freedom, but our rotation has 3 degrees of freedom and our translation only adds 3 more. So we only have 6 degrees of freedom. What this means is that if we decompose the homography, we get up to 4 possible solutions. And typically you can easily discard 2 of them because they will be behind the camera. So you can simply take a look on the translation vector and identify those. However, this leaves us with 2 solutions in front of the camera. And this is an ambiguity which we cannot easily resolve. It is also the reason for the flipped coordinate system of the one marker we've seen earlier. So let's recall that. This was over here one possible solution, and this is another possible solution. And this is not, like I said earlier, it is not a problem of bad corner precision, but a general problem of homography decomposition. And it generally can occur if the size of the marker is much smaller than the distance of the marker to the camera, which is the case here. In this situation, most of the perspective cues are removed, and then only noise decides which of these 2 solutions get preferred. And the perspective endpoint formulations neither helps with this, as you can see with the markers. Therefore, in OpenCV, an additional function was introduced, which is solvepnp generic, which does not return only one solution, but a vector of solutions to specifically handle the case where there are multiple possible solutions. And then you as a user are responsible to pick the right one with some additional information which the function cannot know. So for instance, with the markers, we had multiple of them and most of them were correct. You could then use the other detections to pick the correct solutions using solvepnp generic. And speaking of OpenCV, a hint: if you use decompose homography mat, this function assumes that both images are projected. So both are taken by a camera with a camera matrix. And this is not true if you use natural feature detection, where one of the images is simply a template. So for this reason, you have to modify the homography you decompose by this function as follows. You have to multiply it by the inverse of the intrinsic from the right side or the left side, depending which of the 2 images is your template. Okay, let's recap the natural feature detection with this. So first we have to detect points of interest and compute descriptors for them. And this is in the order of 100 until 1000 of points per image. And then we have to match these detected points with a template using k-nearest neighbor search. And afterwards we have to filter outliers. First using the ratio test, which is rather cheap, but then we also have to do RANSAC, which is more involved. And if we do it for every frame, this incurs a high computation cost. So the whole pipeline will be slow. To speed things up, we therefore would like to reuse the information if we detected the template in one frame for the next frame. So yeah. Use information from the previous frame, and this leads us to tracking. With tracking, you no longer detect the template from scratch in each frame, but rather rely on the previous location. Or if we want to define it a little bit more formally, it's the following situation. With detection, we search for a global solution. So no matter where we start searching, we always want to arrive at the global minima. So this is the detection situation, and we look always at the whole function. For tracking, however, we only look at the limited range around a certain starting point. So with tracking, if we start in this yellow region, we only arrive at this solution and will never get to the global minima. Which is, however, by design, because with tracking we want to assume that we are already close to the real solution. So detection and tracking have different goals. With detection, we are interested in the global solution, and we are willing to invest a high computation time for this. However, in this setting, it's okay if we end up somewhere close to the global solution and let's say not with subpixel accuracy. With tracking, on the other hand, we are only willing to invest low computation time, but still we want to arrive at the high precision. So if we assume that we are already close at the true solution, then we want to improve the precision and as fast as possible. There are several tracking algorithms available, and the most prominent is probably the Lucas-Canade feature tracking algorithm. But we want to turn to a different one, which is not so famous, so you get to know it as well. For this, we go back to our marker detection example, but this time we want to track the marker and not detect it anymore, which looks something like this. We assume that we know this location from the previous frame, which is denoted in green here, and now we want to go from the green frame to the new location in the frame we see right now. And for this we want to take advantage of this clear edges our markers have. And this leads us to the edge tracking algorithm, which was introduced by Harris. It's the same guy who was responsible for the Harris corner algorithm. And the edge tracking algorithm works as follows. If we know the edges in the previous frame, then we look orthogonal to the edges to find the locations in the new frame. So let's say we start here and then we walk a line along the blue line and look where we find the edge in the image gradient. And in this case, it would be here. And we do not do this only at one location, but at several locations. You might think, okay, this looks much more complicated than the image before because we have all these orthogonal lines, and now we have to walk the lines and look for the edge. However, this is actually fairly simple. And for this, let's take a different view on this same situation, like this. Here, we simply took all pixels covered by a line and drawn them horizontally, and then we took the pixels from the next line. So this is all the lines stacked together over here. And in this view, the green border is in the center of the line. So this is just a different view on these lines. And over here, you can see all the lines from this lower corner of the marker, and over here you see all the lines from the upper corner of the marker. So the lines are oriented always from inside to outside. And in this view over here, it's much simpler to find the edge, because now we only have to walk left or right until the gradient is strong enough for ours. The important thing is that we choose the closest location to the center and not any location, because over here, for instance, we have the inner part of the marker here, but we want to pick this the outer contour. And on this slide, we see the locations we actually chose in yellow. And as you can see, we picked the correct ones, except over here we picked the inside of the marker, which was wrong. But nevertheless, we can now use these yellow pixels and draw them in our camera frame, because there's a one-to-one mapping between the lines over here and the lines over here. Like this. So our new situation is that we know for all 2D locations from the previous frame, the new 2D locations in the current frame. And if you recall, we know the 3D locations of the marker corners as well. This means we can also interpolate the 3D locations along the edge. So we now again have a simple perspective endpoint problem where we have this yellow 2D measurements and the origins of the blue lines. We know the respective 3D coordinates as well. However, this is a slightly more specialized setting. We have an outlier over here, so let's take a look at the PNP problem in more detail. Because we have outliers, we must use a robust function, and the only robust function OpenCV currently offers for this is the PNP ransack method, which does ransack with all the correspondences you give it. However, this is rather slow because it computes the solution from scratch for each ransack iteration. A better solution is the solve PNP refine method, which uses a starting solution which you give it, and in the tracking scenario we know a starting solution, and then it only tries to refine it. However, this method is not robust because it's using the L2 norm internally, which gives a high importance to outliers. Instead, one should use a more robust norm like the Huber function. However, it is not implemented in OpenCV yet. So probably you have to go with a slower ransack method. Okay, so let's say we apply this ransack method. How does our improved pose look like? It looks like something like this. Now our green marker contour moved here, and as you can see, it's not quite exact. One of the problem is that the orthogonal direction to the contour is not quite valid with the marker. So what can we do about it? Well, we can use this solution and start over again like this, and simply do another rapid iteration. And because we are now closer to the true solution, it will give us a better result, as you can see here. And this one is pretty good already after 2 rapid iterations, and actually the computation we did so far is far less than we had to do to detect the marker initially, and this pays off especially if you have high resolutions images. The nice thing about the rapid approach though is that it extends naturally to 3D objects and is not restricted to this 2D markers. So let's zoom out a little bit and take a look at the car, which we want to track similarly to the marker. In green, this is like the position it had in the last frame, and as you can see, it's not quite exact. And on the right hand, you again see all the search lines tagged together in the search bundle. This is what this view actually is called. And if we do several rapid iterations, 5 in this case, we end up here, where the car 3D model is much better aligned with the camera frame. And you can see this on in the search bundle, because the car silhouette is now aligned with the center in the search bundle. So you have this red car regions on the left most of the time, except for the wheels. There the search lines seem to be oriented in the wrong way, but let's ignore this for a second. If we can assume that all the inner regions of the car are on the left and all the background regions are on the right, we can now improve upon Rapid by taking advantage of the appearance. Like so far, Rapid only cares about the gradient intensity, so it does not matter whether it's a gradient between white and black or white and red. However, if we can assume that the car is red, we can also consider this when searching for the gradient. So we would discard this one here and always search for the red in the search bundle. And this is actually the direction where the more recent approaches which build upon Rapid go. They try to segment this search bundle into inner parts and outer parts. And like most current approaches do this by color. They compute histograms on the inner regions and on the background regions to separate these two. But the goal was only to give you an idea how Rapid works, and this is why we will not cover any more advanced approaches here. And with this, I want to close the lecture, and I hope you could learn something. Thanks for listening.